So let's have a look at problem 16.3. What we have here is a feedback loop with g of s equal to either g1 of s, which is this one here, or g2 of s, which is this one here. And the idea is to look at the sensitivity function s for different values of controller gains k. So k here is just a static gain, and three different values of gain are given here and here. So the core idea in this exercise is to see how the sensitivity function changes as we increase the gain, and the waterbed effect becomes evident, which you've seen in the lectures. And let's see that now. So we have two different transfer functions, g1 of s, g2 of s, and static gains k for this feedback loop. Now before we take the first one, which is g1, let's quickly review some preliminaries. So let's define the open loop transfer function L, which is defined as k times g, that's y, that's e, that's r, and that's the standard loop that you see here. But now let's introduce a noise channel here. If we do that, and by the way, this is a negative feedback loop, and let's say this is plus. So this is quite arbitrary because the noise could be positive or negative. Let's just call it plus. Now this loop is the same as this loop. If I pull the noise in here and I call this thing r minus the noise as some r tilde, and then this is e. So I've just pulled in the noise here. So now let's calculate the transfer function from r tilde to e. So we have e is r tilde minus y, but y is le, so r tilde minus le. If I bring this to the other side, I have e as 1 over 1 plus l times r tilde. And now r tilde is composed of r and n. So what we have is the transfer function from r and n to error e is 1 over 1 plus l. Similarly, we have from this equation, because y is just le and e is this times r tilde, we have l over 1 plus l times r tilde equal to y. So what we have is the transfer function from r or n to y is l over 1 plus l, and that's again because r is composed of r tilde is composed of r and n here. So the transfer function from r and n to y is this one. Note that we have this negative sign here. That's really not that vital, because the noise can simply be negative or positive, so that's just arbitrary. So we call this guy 1 over 1 plus l the sensitivity transfer function, and we denote this by l, and we call this guy the complementary sensitivity, and we denote this by t. And we can clearly see then that s plus t is 1 plus l over 1 plus l and 1. So that's the key relationship between sensitivity and complementary sensitivity, and that also explains the name. So what we roughly want roughly speaking, is that for frequencies we want to drag, or in other words, for frequencies where we expect the reference signal to be, we want the complementary sensitivity S to be almost equal to 0, which would mean that the error is almost equal to 0, and therefore also the T to be almost equal to 1. On the other hand, what we want is for frequencies we want to reject, or in other words, for frequencies where the disturbance or the noise N lies, we don't want to track those, or in other words, we want the T to be almost equal to 0, and therefore the S to be almost equal to 1. So this is what we roughly want, and let's see how increasing the gain now sort of shows us a trade-off between these two goals that we desire. So let's take the first transfer function, which is g1, 2 over s times s plus 1. So now g1 of s is 2 over s times s plus 1. Let's quickly note that this is marginally stable. That's because we have one integrator here and one stable pole at -1. Also note that this is strictly proper with pole excess of 2. So there are 2 poles and no zeros, so the pole excess is just 2. And now let's investigate what happens to this transfer function in the feedback loop. So now we consider the feedback loop 2k over s times s plus 1, that's our L now, in feedback, in negative feedback from R. Now before we look at the sensitivity and the complementary sensitivity, let's quickly use some tools to have some tools from our earlier control courses and have some idea about what we might expect for this feedback loop. So what we have is 2k over ss plus 1. So the closed loop system, which is T, so we have R T, which is then L over 1 plus L, which you can compute. So let me just write down here, L over 1 plus L2, so that's our y, and T is 2k over s square plus s times s square plus s over s square plus s plus 2k. So that would get cancelled, so you would have 2k over s square plus s plus 2k. That would be the closed loop transfer function from R to Y. Now the closed loop poles would be given by the roots of the quadratic equation given here, because that's the characteristic polynomial, and we can then just say that the roots or the poles are at -1 plus minus, using the quadratic formula now, b square minus 4 into 1 into 2k divided by 2. So that's just minus half plus minus. Now I'll put the 2 inside, so that will be 1 over 4, that is half squared, and the 4 will get cancelled to get minus 2k. So that's just basic things that we learn in earlier control courses. So what we know that for k negative, so if k is negative, then this, so k is negative and this term would be positive, and then this term would be greater than half squared, so the square root would be greater than half, so we would have at least one pole in the right half plane, so unstable. So k has to be positive or 0. Clearly if k is 0, then we have open circuit, so we don't have a feedback loop anymore. So k has to be positive for stability. And actually we can say a bit more, because for lower values of k, so we can just check when the square root sign, so when the discriminant or the term under the square root sign is 0, and that's 0 when k is 1 over 8. Because if this is 1 over 8, that would be 1 over 4, and that would cancel. So for any k between 0 and 1 over 8, we would have this term less than half squared, and that would mean we would have real poles. And for k greater than 1 over 8, we would have imaginary poles with real part at minus a half. So if we then just show this in the complex plane, the closed loop poles would look something like this, the root locus. So we would have something like this, and then we would have imaginary poles, so that would be minus a half for, and that would be the value of k equal to 1/8, and this would be smaller values of k, and these would be larger values of k. So now let's look at the values given to us. So we have k equal to 0.1, 1 and 10, 0.1, 1 and 10 for G1. So for 0.1 is 1 over 10, which is smaller than 1 over 8, so this could be k1. So let me just say k1 equal to 0.1. Then we have, I think, what was it, 1 and 10. For k equal to 1, we would be somewhere here, and for k equal to 10, we would be somewhere higher. So remember that we would have pole pairs, not just on one side. So what that means is for k1 equal to 0.1, we would see something like a non-oscillatory stable response, but for k equal to 1, k equal to 10, we should see some oscillations, and for k equal to 10, we should see high frequency oscillation. So that's something that we know from earlier courses. I just thought it's a good idea to review this here, so that we gain more insight when we do the sensitivity plots. So that's from root locus, or just basically just the closed loop poles. Now we also learned about Border magnitude plots and Nyquist plots, so let's look at that as well. So L now is 2k over s plus 1, and if we try to sketch the border plot or the border magnitude plot of L, we would get we have we have integral action, so we would have a slope of minus 20 dB per decade here, and then we have a pole at a stable pole at s equal to -1. So at this one we would increase the slope. So that would be a sketch of the border plot for L. Similarly, the magnitude plot, so the phase plot would look, so that would be the angle of L of j omega, would start, because there is a pole, would start at -90, and then it would, oh, that's drop to -180. After the pole. So that's a sketch of what we would see with the L border plot. And now we can also sketch, using these border plots, the Nyquist diagram. So let me first bring these things here, and let's sketch the Nyquist plot here. So what we know is that we start at -90, so somewhere here, let me use a different color. So we start somewhere here, and we the phase at the end is -180, so be something like this. Obviously the mirror image of this, and then there is this final circle at infinity. Now this is for, let's say, for a given value of k. Now if we increase the k, so let's say this one is for k equal to 1, so use this one, yes. So this one is for k equals to 1. For k equal to 0.1, we would just shift the we would just shift this down, and for k equals to 10, so let me just write here, k equals to 10, we would just shift it above. So I'm sorry, try to draw it better. So it's just shifted versions of k equal to 1. What about the phase? The phase would remain the same, because we're just scaling L. There is no phase change for different scale versions of that one. Now what would happen to the Nyquist plot? So let's say this one is for k equal to 1. For k equal to 0.1, we bring this one we bring this one down. So what would happen is we would just scale this down to something like this. So that would be k equal to 0.1, and for k equal to 10, we would just scale it up, so it would be something like this, and then the mirror image. So what do we want to see here then? So let's see the stability condition. So we had we have to draw show the -1 point somewhere here, and let me try to draw a circle. Yes, so recall the phase gain, the gain phase margin and the gain margins. So what we see is that for arbitrarily large values of k, we would really never encircle the point -1. We would always have something like this, so the scaled version of this. So we would never really lose stability. So what we see from the Nyquist plot is that for k any large k, so for k however large, we don't lose stability, but what we do lose is the phase margin, because what you can see is that the point where the Nyquist curve intersects this circle. So for example, let's look at k equal to 0.1, which was this one, this curve here, this point or this point. So this is the phase margin. So what this means is you would have to rotate this by this angle in order to lose stability, and that you can see in the Bode magnitude plot by looking at the 0 dB line. This is the intersection, and if you see, so this figure is now not to scale, but that difference would be the phase margin, and the lower you make this, the sooner it will intersect the 0 dB line, and the higher the phase margin we would have. The gain margin in this case is infinite, because we can just scale this, as we just said, scale this however large, and we would still have stability. So that means we have infinite gain margin, but poor phase margin for higher values of k. And in some sense we saw that in the root locus already, that if we have any k positive, we would always be stable. But for larger values of k, we would have high frequency oscillations, and in the Nyquist plot we see that for higher values of k we have a poor phase margins, so a small phase lag could make the loop unstable. So this is again just a review. So let's look at some results. So here I've plotted the so these were the sketches, hand-drawn sketches. Now I've plotted the Bode plots in the Nyquist diagram for the three different values of k. You see, as we just discussed, we just have translated up and down versions of the magnitude plot. The phase plot remains same, and we have these dark lines as phase margins here, here, and here. And you see that for larger, if we have k3, which is 10, this intersects the 0 dB line here, and we have a poor phase margin, whereas for a lower value of k of 0.1, we have a large phase margin. We also see this in the Nyquist plot. So these are also what we just discussed. So as you scale the k up, we scale these things up, and the -1 point is shown here. However large you want to scale this, you will never encircle the -1 point, so you never lose stability, but you do lose the phase margin. So you lose robustness against delay, for example. So because delay sort of affects the phase. So that's the Nyquist and the border plot. So this is just the zoomed version here of this one. Now let's plot finally the sensitivity plots for the three different values of k. So here are the sensitivity plots. Let's first quickly recall that the sensitivity S is the transfer function from R to E, and the complementary sensitivity is the transfer function from R to Y. So let's make some observations here. So first of all, we see that at low frequencies we have a slope of about 20 dB per decade, which means that if we have step references, we would have zero steady state error. So that's basically saying that we have integral action and zero steady state error for step references. And that can also be seen here, because for step inputs you have t equal to 0 dB, which is just 1. So then the y at the steady state will be exactly equal to r steady state, and if it's a step, then r is just constant, and then y would be equal to r. So that's one observation. Then we see that if we had, for example, a sinusoidal input, say at this frequency, we see that we see that the error would be the least for the blue curve, which is corresponding to k3 equal to 10, and the error would be large for k1 equal to 0.1 or k equal to 0.1. So this means that if we increase the gain, we would have good tracking performance at low frequencies. But now let's see what happens at high frequencies. Typically at high frequencies we have the noise. So let's also bring in the noise here. So if you have a noise which is typically assumed to be at high frequencies, say here, that's around 5 radians per second, let's say 5 units. Then we see that this noise would correspond to a high error for k3 equal to 10, but that would lead to a relatively low error for k1 equal to 0.1, which means that if we have a high value of gain, we would have noise amplification or high frequency noise amplification. Yes, so this is basically what we want to see. Another small thing is that we see that the bandwidth, as we increase the k, is also increasing, and as we just said, this is at the cost of sort of poor noise, high frequency noise rejection. So let's really check this by inputting sinusoidal inputs to this feedback loop to observe or to verify what we just observed via the sensitivity and the complementary sensitivity plots. So here you see what we've done is we have new noise. So let me use the same notation. So there is no noise injection, but we have a reference, and that should be tracked with a relatively low frequency. So what we see is that for k1 equal to 0.1, which is the red one, so you don't see the reference here actually, but it's just a sine wave quite close to what you see in the blue and the green curves. You have this reference, and what we see is that the red curve is not quite tracking the reference as compared to the blue and the green curves, and that's because what we just saw here. So this frequency is 0.05, so this is 0.1, so somewhere here. And we saw that here for the blue curve, which is a high value of gain, the error is much lower than the error for when k is equal to 0.1, and that's what you see here. So now let's inject noise. So here you see the simulation results for when noise is injected now. So now we have a 5% noise injected at the frequency of 4.3, which is around here, around the peak. And what you see here clearly is that even though for a low value of gain of 0.1 the tracking was poor, as you saw in this figure, it is not affected by the noise at all, so it simply rejects that noise. Whereas the blue curve, which showed relatively good tracking performance here, is affected wildly by this noise, because the noise is exactly injected at the peak here of the sensitivity. So that's sort of the takeaway here. Now let's also see how the step responses look like. So here you now see the step response for these three values of the gain, and you see that for a high value of gain, k3 equal to 10, we see that we have much quicker convergence, so smaller rise times, smaller settling times, but at the cost of huge overshoots and large oscillations. Whereas for low values of gain we have no overshoots but relatively slow convergence. And recall that we already had some inkling about this after we did the root locus, because we saw that for low values of gain, especially less than 1/8, we saw that we had two real poles leading to no oscillations and an overdamped behavior, which is exactly what you see here. And for higher values of gain we would see high frequency oscillations but a faster response. So that's it for G1. Now let's have a look at G2. So let's have a look at G2 of S now, and that's given by 2 minus S over S times S plus 2. What we see again here, that this is marginally stable because of the integrator and a stable pole at -2. This is also strictly proper because we have two poles and only one 0 at 2, but now we have a right half plane 0. So we have a 0 in the right half plane, and that's called as a non-minimum phase. Zero. So let's again look at L of S, which is the open loop transfer function k times G2 of S, which in this case is now k times 2 minus S over S plus 2. The closed loop transfer function T of S is just L over 1 plus L, which is k2 minus S over S plus 2 times 1 plus L, and that would be S squared plus 2 minus Ks plus 2K over S square plus, so let me just write down the final one. You can work this out. Let me just write down the final one, which is S square plus 2S over S square plus 2 minus Ks plus 2K. Now the poles, so closed loop poles are the solutions of this quadratic equation, and we can see that that is nothing but minus of 2 minus k plus minus k squared 4 times 2k divided by 2. Now you can see, so let me just write it like this, minus of, so pull the minus inside, k minus 2 plus minus, it's a square, 2 minus k squared is just the same as k minus 2 squared minus 8k. Now again, like before, we see that if k is negative, this term would be positive, and then this term would be greater than k minus 2 squared, and then the square root would be greater than k minus 2, and then we would have at least one unstable pole. So k negative leads to unstable pole. K equal to 0 as before would lead to an open circuit, and k positive, however, now based on this term we see that if k is greater than 2, we would have k minus 2 to be positive, and this term would be less than that, so that would lead to an unstable pole again. So k has to be between 0 and 2 for stability. So that's again just from just checking the closed loop poles. So now let's look at, as we did before, instead of sketching now the body and the phase magnitude border plots for L and the Nyquist plot for L, let's just plot it with MATLAB. So here you see the border plots and the Nyquist diagram for k times g2 now. So as before, increasing the gain, so now the gain is increasing from 0.1 to 0.5 to 1.5. Note that this has to be less than 2, because otherwise we just saw from the closed loop poles analysis that would be unstable. So now as the k is increasing, we see that this goes up. With increasing k, the phase remains same as before, but now interestingly, because we have an upper limit on k, we do have a phase margin, and the phase margin is not infinite, and that we can also see from the Nyquist plots. So the Nyquist plots, if you have a look here, so let me just sketch how the Nyquist plot looks like. So this Nyquist plot is basically again coming from minus 90 and then going to 0, not at minus 180 as before, but at minus 270 or plus 90, as you see here. So we have this guy, and now if we just draw the symmetric version of this, oops, we have something like this, and then we have this one, and this is exactly what you see here. But now, because of this looping behavior, we see that if we scale this up, we might encircle the -1 point. So we don't have an infinite phase margin, but we do have a finite one, and that can be seen now here. So if we look at the intersections of the phase plot with 180 degrees, so that is nothing but so if I draw now a circle, so the circle, this is stretched, so the circle would look something like this because this diagram is stretched. So what this means is, let me just sketch a new one just to explain the idea. So if we have a circle like this passing through -1, and now if we have our body plot going like this, if we scale this thing up, we might have an encirclement of -1. And to see the phase margin, we have to look at where the phase is -180, so where this line intersects this line, and how much do we have to scale to move this point to the left. And that in the body plot can be seen like this. So we look at where the phase margin intersects 180 degrees, so at this location, and now at this point we see the gain margins for the three different values of k. So we, for k1 equal to 0.1, this is the gain margin. For k equal to 0.5, they have a lower gain margin. For k equal to 1.5, we have an even lower gain margin. And that's clearly because you know from the previous analysis here that if k is greater than 2, we will encircle the point -1 and we will lose stability, and that's exactly captured in the phase margin here, in the gain margin here, sorry. The phase margin is as before. You look at the intersection of the body plot with 0 dB line and look at this curve. So we have the highest phase margin for 0.1 because this is where it intersects. We have a lower phase margin for 0.5 and even lower. So what we see here is that lower values of k lead to higher phase and gain margins, and vice versa. Higher values of k lead to lower phase and gain margins. And this of course can be sort of remove that part again. So, and finally, now let's have a look at the sensitivity plots for this one. So these are the sensitivity plots and the complementary sensitivity plots, and these look quite similar to the ones that we saw before. We see for all three gains a slope of around -20, a slope of around 20 dB per decade in the low frequency region, and S, recall, is from R to E and T is from R to Y. So for low frequency reference inputs, we have 0 steady state error for all three gain values. Again, if we now have a look at some low frequency response, we see that the lower value of gain, which is the red curve, leads to a higher error than the higher value of gain, which is the blue curve. And we can see the high frequency if we have a noise, because this is also from noise to error, noise to Y. If we have high frequency noise of around 2 uh, units, then we have an amplification for the design with high gain, whereas less amplification for the other two. And let's again quickly look at the results with simulations. So here you see the response for no noise but a reference input of a sinusoidal wave at low frequencies. As before, you see that now here you do see the gray value, the gray curve showing the reference, and you see that the blue curve with the highest value of the gain is tracking it quite well, but as you reduce the gain, the tracking performance reduces. This is again this phenomenon that you see here. And now if you inject noise, so let me bring this here. So now if you inject noise, so now the reference is sine of 0.05t as before, but now I have a noise, again a 5% noise injected at 1.90, which is where we saw the peak around 2. And here you see then that first of all you do see the noise in the gray curve, and you see that this noise is greatly amplified in the design with the highest gain of 1.5, whereas it is not affecting the low gain design much. So let's also quickly see the step response. So here you see the step response for the three designs, and again as before you see a smaller rise time and a smaller settling time for the designs with high gain, but with overshoots and with oscillations, whereas the design with low gain has no oscillations and no overshoot, but it is rather slow. One peculiar thing that you see here is that you see an undershoot, and this is because of the non-minimum phase 0. That's a telltale sign. If you see a step response with an undershoot, that's a sign of zeros on the right half plane. So what is the key underlying idea in this question? And that is as follows: good tracking of low frequency references and good noise rejection at high frequencies are sort of conflicting objectives. And there is a trade-off between these two goals that we typically have in a control design task. So we have basically an inherent limit to what we can do when trying to achieve these two goals. So let me just say a few more words about how do we see this in the sensitivity plots. So what we really want is to have So let me just sketch this thing here again. So in the sensitivity plots, what we really want is in the low frequency region the sensitivity to be quite low, and in the high frequency region we want the complementary sensitivity to be quite low, or the sensitivity to be 1 but not more. So we want to sort of push this down and not allow, ideally, so this so let's say this is the, let me just say what I'm sketching here. So this is the frequency axis and this is S of j omega, and this is the 0 dB line. So what we want is to push this thing down, but without letting this one up, and there is an inherent limit to what we can do, and that's given by the waterbed effect. And what it says is that if we have a pole axis of of 2 or more, or if we have a non-minimum phase zero, we would have a peak in S at high frequencies. And this is, as you saw already in the lecture, made plausible by the Nyquist plot. Let's quickly look at the Nyquist plot. So this Nyquist plot clearly shows that here for this is the second example. Here we do penetrate the disk. So let me just draw it in the sketch that we already had, or let me just draw it here below. What we see is that S is 1 over 1 plus L. Now if we have -1 point here, and if we draw a circle around it, we saw that both Nyquist plots penetrated this circle, and this circle sort of represents all points in the complex plane with distance 1 from the point -1. So if the Nyquist plot of L, in the two examples we saw that in the first example it was something like this, and in the second example it was something like this, and in both examples we saw that this Nyquist plot of L penetrated this circle, which means that the distance of L of j omega from 1 at some high frequency was less than 1, and if the denominator is less than 1, there is a peak in S. So S will be greater than 1, and that's why you see a peak here in all our in both our examples, and that's basically the idea here. So, and this is called the waterbed effect. So that's it for this problem. Thanks a lot.